Okay, so today we're going to prove the Cauchy-Schwartz inequality, which states that for any x and y contained in R to the n, the absolute value of x dot y is less than or equal to the norm of x times the norm of y. Now, before we get started on how the dot product is defined and how the norm is defined, remember if x and y in R to the n, x has this form, right? X of 1, x of 2, x of n, and y is equal to y sub 1, y sub 2, y sub n, where each individual component is a real number, right? So now that we have that idea, let's go ahead and look at the dot product of x and y. We know that's equal to the sum from 1 to n of x sub I times y sub I. And we can also say that this is the same thing as x of 1, so x of 1 times y sub 1, plus x of 2 times y sub 2, so plus dot dot dot, plus x of n times y sub n. So notice we multiply each corresponding component and we add those together for the dot product. The norm is defined as the square root of the sum from 1 to n of x of I squared, which is the same thing as the square root of x of 1 squared plus x of 2 squared, all the way to x of n squared. And lastly, we want to identify the 0 in R to the n, which is typically denoted by theta. And this theta is just each component is equal to 0 n times, right? So that's basically what we need in order to show this inequality. So let's go ahead and start the proof. And the first case is going to be if one of these guys is the 0 element in R to the n. So let's go ahead and do that. So x or y is that 0 element. So the proof's going to be the same whether or not we choose x or y to be that 0 element. So without loss of generality, we're going to assume that x is equal to that 0 element. So let's go ahead and start with the piece we want. The absolute value of x dot y is going to be the same thing as the absolute value of the 0 element in R to the n dot y. And we know, using the dot product, this is equal to the sum from 1 to n of 0, right? Because every component in that 0 element in R to the n is 0, times y sub I. And then we can just rewrite this, right? We can rewrite this as 0 times y sub 1 plus dot 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 plus 0 times y sub n. And we know this is just going to be the absolute value of 0, which is 0. And we want the norm of the 0 element R to the n and the norm of y. So surely we can say this is equal to the square root of 0 squared plus 0 squared plus dot 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 plus 0 squared n times, right? Times the square root, because this will just be 0. And 0 times anything when they're real numbers is 0. This will be y sub 1 squared plus dot 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 plus y sub n squared. And this is the definition of the norm of the 0 element R to the n times the norm of y. And we established that x was that 0 element in R to the n. So this is equal to the norm of x times the norm of y. So we've shown that the absolute value of x dot y is equal to the norm of x times the norm of y whenever one of these is the 0 element. So surely if these are equal, then we have our inequality that the absolute value of x dot y is less than or equal to the norm of x times the norm of y. So now we're going to look at the case where neither of them are the 0 element. So case 2, x and y are not that 0 element in R to the n. Then we know for each I, and of course I is the index from 1 to n, right? 1, 2, 3, 4, 5, all the way to n. We know that this inequality is true. So let me go ahead and write this inequality. We know that the absolute value of x of I over the norm of x minus the absolute value of y sub I over the norm of y squared is bigger than or equal to 0. Because we know that this is a real number, and then minus this is a real number, so this whole thing is a real number, and we know any real number squared is going to be bigger than or equal to 0. Now, we use this inequality to get our Cauchy-Schwartz inequality up here. Okay, so let's go ahead, and of course, this x of I and y sub I just represents any component in x, which is an element in R to the n, and any component y in for the element y contained in R to the n, right? So this works for any one we choose, right? Remember, x is equal to x of 1, x of 2, x of n. So any one of these that we pick, and the corresponding y, right? Y sub 1, y sub 2, y sub n. Any of these that we pick, where I is either 1 or 2, this inequality works. Okay, let me go ahead and get rid of this. Okay, so now we're going to do some basic math right here. So we're going to distribute this. So this whole distributed will be the absolute value of x of I squared over the norm of x squared minus 2 times the absolute value of x of I times the absolute value of y sub I over the norm of x times the norm of y plus the absolute value of y sub I squared over the norm of y squared is bigger than or equal to 0. Right? This is just completely distributed. Now, what I know is I can add this term to both sides and the inequality will still remain. So if I add this term to both sides, I'll have... So, and another thing to keep in mind, the absolute value of any real number squared is just that real number squared. So this is the same thing as x of I squared over the norm of x squared plus the y sub I squared over the norm of y squared. And that's going to be bigger than or equal to 2 times the absolute value of x sub I times y sub I all over the norm of x times the norm of y. All right, so what we can do now is, instead of writing it like this, we know the absolute value of a real number times the absolute value of a real number is just the absolute value of this number times that number. So let's go ahead and fix that here. Let's see, let me get rid of that. So I know that this is the same thing as x of I times y sub I. Okay, so remember, these i's represent any component in x, which is in R to the n, right? So if this inequality is true for any of those components in x and y, surely the sum of all those components with this is the same. So this is what I mean. This implies that the sum from 1 to n of x of I squared over the norm of x squared plus y sub I squared over the norm of y squared, that sum of all of these components in x and in y is going to be bigger than or equal to the sum from 1 to n of the absolute value of x sub I, y sub I, over the norm of x times the norm of y. Right? Oh, 2. Can't forget that 2, right? Let me fix that really quick. So that 2 right there. Okay, so now we're going to use some properties of finite sums. So we know the sum of this sum is the same thing as the sum I equals 1 to n of x of I squared over the norm of x squared plus the sum I equals 1 to n of y sub I squared over the norm of y squared. And this is going to be bigger than or equal to. So we know that 2 over the norm of x times the norm of y is a constant in all of these terms in the sum, right? So what I can do is I can just factor that out because it's always the same for each term in that sequence. So this is the same thing as 2 over the absolute, or not the absolute value, the norm of x times the norm of y times that sum from 1 to n of the absolute value of x of I times y sub I. Okay. And of course, we can do the same thing here, right? We know that the norm of x squared and the norm of y squared are both constants in all these terms in the sequence. So I can factor those out as well. So this is the same thing as 1 over the norm of x squared times the sum from 1 to n of x of I squared plus 1 over the norm of y squared times the sum from 1 to n of y sub I squared. And that's going to be bigger than or equal to 2 times the norm of x times the norm of y times this sum from 1 to n of x of I, y sub I, the absolute value. All right, so now we're going to do a little bit of a deep dive. We're going to look at this left-hand side of this inequality here. So let me go ahead and rewrite that here. Well, we know that 1 over the norm of x squared times the sum from 1 to n of x of I squared plus 1 over the norm of y squared times the sum from 1 to n of y sub I squared. This is the same thing as, so equals 1 over the norm of x squared times the square root of the sum from I equals 1 to n of x of I squared, right? So this, since we know this is going to be positive, right? This sum is completely positive. Then we know the square root. So if we take the square root of this and we square it, that is the same thing as this because all these terms are positive. So we're only messing with positive. And we know that's the same thing for over here. 1 over the norm of y squared, same thing here. So the sum, or the square root, right? The square root from 1 to n. Well, let me do a better job with that. Let me get that going. So the square root, the sum from 1 to n of y sub I squared square. And the reason why I did that is because the square root of this sum from 1 to n of x of I squared is the norm of x, and the same thing for this. This is the norm of y. So this is equal to 1 over the norm of x squared times the norm of x squared, because this is the norm of x, and then we have that square, right? Plus 1 over the norm of y squared times the norm of y squared. And then 1 over the norm of x squared times the norm of x squared is just 1. And then this is 1 as well. So 1 plus 1, which is 2. So we know that this side of the inequality is just 2. So we have 2. We know that 2 is bigger than this right here. So let's go ahead and put that here. So this implies that 2 is going to be bigger than or equal to, let me look up here, 2 over the norm of x times the norm of y. So 2 over the norm of x times the norm of y times that sum from 1 to n. I believe it is the absolute value of x of I times y sub I, which is what we want, of course. Let me make sure. Yep. All right. Now, what I can do is I can multiply both sides by the norm of x times the norm of y over 2, right? So if I were to multiply both sides by that, I would get the norm of x times the norm of y is bigger than or equal to the sum from 1 to n of the absolute value of x of I, y sub I. Right? And then let's expand what this is, right? So this means that the norm of x times the norm of y is going to be bigger than or equal to x of 1, y sub 1, plus x of 2, y sub 2, all the way to x of n, y sub n. But I know by the triangle inequality that this here, so by the triangle inequality, I know that the sum of these guys here is bigger than x of 1, y sub 1, plus x of 2, bigger than or equal to, of course, y sub 2 plus dot 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 plus x of n, y sub n, right? And this is equal to the sum from 1 to n, well, I guess the absolute value of the sum from 1 to n of x of I times y sub I. And this just so happens to be that dot product, x dot y, which is so cool. We got that the norm of x, so let me go ahead and write what we got. We got the norm of x times the norm of y, right, is bigger than or equal to x dot y. And that's exactly what we wanted to show. Look, all the way up here, right? The norm of x times the norm of y is bigger than or equal to the absolute value of x dot y. We can, of course, rewrite it exactly like that, right? This is the same thing as x dot y is less than or equal to the norm of x times the norm of y. So when both of them are not the zero element in R to the n, we know that it is less than or equal to the norm of x times the norm of, well, the absolute value of the dot product is less than or equal to the norm of x times the norm of y. And that is Cauchy's inequality, which is useful for later discussion on metric spaces.